I'm thrilled to be here, and let's get started. I don't want to say too much. So I'm going to be talking about exploding stars. That's what I study in my research, and I'm going to talk about its connection to life and the universe and everything. And so here's the outline. You can see it's very simple. Actually, so here's the serious outline. This is the stop throwing things outline. I'm going to talk about how stars die. So the first part of the talk, we'll be talking about how stars die and how some of them explode. I'll be then talking about how that's exploding stars, the remnants of those are the cradle of life. And then I'll talk about what else we get from exploding stars. Then I'll talk about how exploding stars reveal the fate of the universe. And then I'll summarize everything, because life in the universe, well, is there anything else? The answer is no, that's everything, right? So let me start by talking about what is a star, right? The modern ideas around this date to around 1910, when Hertzsprung and Russell made a diagram that is very famous. It's called the Hertzsprung-Russell diagram, HR diagram for short. They made on the y-axis, the vertical part, how bright the star is, and on the x-axis is the temperature of the star. And in fact, when they were doing this, they did it by color, and so they did it the blue ones on the left and the red ones on the right, and so that's actually high temperature versus low temperature. So it's backwards, and because it's astronomy, nothing ever changes. Once a mistake is made, it's sort of fixed forever. And so that's what happens. And so we still make the HR diagram that way today. Here I've made it for about the 50 stars that are nearest to the sun, right? The nearest to us. The sun is the yellow one there in the middle. Alpha Centauri is a lot like the sun. It's the one just next to it. The brightest star in the sky, Sirius, as you can see, it's up on the sort of the upper left corner, heading towards the upper left corner. Sirius actually is a double star. It has a companion star. The bright one you see is Sirius A. The one you can't really see unless you get a big telescope is Sirius B, and it's down in the lower left corner. And I picked one well-known star, Betelgeuse, the left arm of the Great One, prominent star in the Orion constellation, and it's over in the upper right. You can see that they fall into three distinct groups. There's the slash across the middle. There's the ones in the upper right and the ones in the lower left. Right, so what's going on here? So the slash down the middle is got most of the stars fall into that slash, about 90%. It's called the main sequence, right? And it was understood by Eddington in 1924 and Bethe in 1939. Eddington basically described what's going on and why it has the bends in it and all this other stuff. He did all this stuff without having any idea what the power source of stars were. Right? He did not know that nuclear energy, fusion of hydrogen into helium, was the basic power source of the stars, and it was Bethe who wrote that all down in a truly seminal work in 1939, describing that. Basically, it's the main sequence stars are stars that are fusing hydrogen, which is the most abundant element in the universe, into helium in their core, right? And why there's a spectrum of them is because of how it works. A star is a balance between gravity, which is trying to pull it all in and collapse it, and the central energy production, which is pushing back out. It's making radiation that pushes back out. So a heavier star, more mass in the star, has stronger gravity, so the center has to be brighter and hotter to push back out and stop the collapse. right? So the massive stars have to burn hotter and brighter to stave off gravitational collapse. So you can also see, and we can show that, right? We can show that that's what's happening in this main sequence. Okay, so you're looking at a spectra, and the spectra is of this light bulb here that you can't see. And I'll turn on the light bulb, and I've turned it on at sort of a low level, right? And you can see at this low level, it peaks sort of here around, I don't know, a little above 660 nanometers, right? That's, we'd think of that's kind of heading off towards the red. Now I'm going to make it hotter. And one thing you should see is it gets a lot brighter as it gets hotter. And then the peak moves over to shorter wavelengths. And so it gets bluer. That's exactly what's happening with the main sequence stars. You can see what happens, right? The low mass stars, so something that's a small star and it's got a red color because it's over on the cool side there, like Proxima Centauri. These are called red dwarfs, and they're the most abundant type of stars in the universe, right? And then you move up the main sequence, and you can see its mass is about 1/10 of a solar mass, right? You move on up to the sun, for example, which has 1 solar mass. It's a yellow star, and it burns hotter. It's burning hotter and brighter. And then you go up to a very bright star like Sirius, the brightest star in our sky, about 2 solar masses, on up the spectra, on up the sequence. And the sequence also shows how long these stars will burn, right? They're consuming their hydrogen in their core, and it'll eventually run out. For the red dwarfs like Proxima Centauri, it burns for 1 trillion years. The sun, about 10 billion years. Right? And a star like the heavy stars, some handful of millions of years. Right? So very long on our time scales, and you can see quite a difference as you move up. So what happens when you run out of the fuel in the center? Well, the star begins to collapse. Right? It's no longer burning. So gravity starts to win, the star starts to collapse. But that makes the center denser and hotter. And so that allows you to start burning the heavier elements, right? It's easiest to burn hydrogen, but if you're denser and hotter, you can start burning the heavier elements. And helium is what's produced by the burning of hydrogen. So helium starts burning. And the whole star gets hotter, so hydrogen fusion actually starts in the outer parts of the star. Right? So, and that causes, when stuff starts burning in the outer part of the stars, that starts the star to get bigger. The outer part becomes less dense, and because it's bigger, it's further away from the heat source, and it cools off the outer part that you actually see. And so you end up with what's called a red giant. And so you can see those stars that I circled over there in the upper right part of the diagram. Well, they're bigger, right? They're bigger because, look, for the same temperature, they're producing more light. They're brighter. And so they have to be bigger. That's the only way they can do that. Right? So they're big and they're red. So they're red giants. Very, very clever name. Once all that starts, the collapse stops, and the star becomes semi-stable again. And here I've got a plot of how much you can get out of burning elements, right? And down in the bottom there, this is the complicated thing called the binding energy, but basically, if you go up, you get energy, right? So going from hydrogen to helium produces a lot of energy. That's the only really good one on the plot, right? When you go from helium, well, the next sort of step up is to carbon. And you can see it's a much smaller step than the step from hydrogen to helium. So you don't get a whole lot of energy by burning helium and turning it into carbon. And so the star, and another thing is the burning isn't terribly efficient. So you may have burned hydrogen for billions of years, but you don't have a whole heck of a lot of helium to start burning. So the star, this is bad news for the star, right? And eventually the helium runs out. And so when the helium runs out, you start burning. The next most favorable one is to start burning neon, et cetera, et cetera, et cetera. Right? The ash of this burning is iron. You can see that's the one at the top of the plot there. once you start producing iron, you got nowhere to go. You cannot get energy out of this iron anymore. And so ash, the iron ash begins to accumulate in the center of the star as it burns these heavier and heavier elements. This table shows really nicely the story of a 25 solar mass star. It can burn hydrogen. You can see how hot it has to get. Tens of millions of degrees Kelvin. At this scale, it doesn't matter. That's the same as the Celsius scale. How dense it has to be, that's only like 5 times denser than water. That's not terribly dense. That's not so bad. That's easy to make. We can do that in the lab, no problem. And it does that for 7 million years. But for helium, well, it's got to get almost 10 times hotter. The density is now really, really high. That is, that's so much it would be, the teaspoon would weigh like a kilogram, right? So 2.5 pounds or something, a teaspoon of this material. So that's like crazy. And then it only can do that for something less than 1 million years, right? And then it turns to carbon, burning carbon. It can only do that for 600 years, essentially a blink of time. Neon for about a year. Oxygen for about 6 months, and silicon for about a day. Right? So once the star runs out of hydrogen, it's really on a downward path, downward unhappy path. At the end, just before the end, it looks something like this. It looks like an onion. Iron ash is accumulating in the core, and it has various layers where it's burning stuff. There's a silicon layer, etc. Various fusion layers out to a hydrogen fusion layer way away from the core. What happens next to a star depends on its mass. So one path for the light and medium stars, so the red dwarfs and stars like the sun, which are low and medium mass stars, is it stops burning. The outer parts of the star are still burning, and that leads to pushing away the outer parts of the star. And this is one thing that's not completely understood exactly how this works. How exactly does a star lose its outer envelope when it gets to this stage? But I'll show you that we see it happening. And what's left behind is the hot, dense core. Right? This hot, dense core is what's left over, and that hot, dense core is called a white dwarf. And it's called a white dwarf, again, because if you look at the HR diagram, these guys down here in the lower left, well, they're hot. See, they're over on the blue and purple side of the plot. So they're when you actually look at their spectrum, they look like flat over the visible, and that makes all the colors of light, and so that looks like it's white. So these stars look like they're white, and they're much smaller because, again, they produce much less light compared to the burning stars in the main sequence. Right, so the white dwarf is the name of these stars. We actually see this happening. These are some pictures from the Hubble Space Telescope of things that astronomers call planetary nebula. You can see at the center of each is a hot white thing. It's a white dwarf. Surrounding it is the outer layers of the star it used to be being blown off. And it's interacting with in these pictures, it's interacting with the interstellar media to make the beautiful pictures you see. And they all look different because the interstellar media around any star is different, right? And so sometimes it's very close and dense, and so the interaction starts right away. Sometimes it's far away, etc. It can have different layers. There could be a dense layer followed by a not dense layer, and then another dense layer, so you get kind of a structure to it. These are among the prettiest things in the sky. They're called planetary nebula because when they were first observed, astronomers thought that these were star systems being born. Right? They thought, oh, this hot, dense star, that's what a star starts as, this hot, dense thing, and then it's gathering in stuff, and out of that dust cloud around it, it will form planets and stuff. We come to realize that that's just wrong. That is, these are not what these things are, but because it's astronomy, you can't change the name because that's what was originally decided. There was planetary nebula. But this is the death of a low or medium mass star turning into the white dwarf. The white dwarf Well, you'll have this big this hot thing. It's typically a good fraction of a solar mass, very hot, no way to cool down, right? It's sitting in vacuum, so it takes it a long time to cool down. So they last for billions of years glowing white, gradually getting cooler and cooler and cooler until eventually they'll turn into an object that we call a black dwarf. Not radiating heat, dead. Okay, and we'll come back to those a little later. This is the filled out HR diagram, right, where you can see a whole bunch of stars are on this, not just the 15 nearest. Some of your favorites are on there. This diagram is very dense with information. You can see, this one really doesn't show how many red dwarfs there are. They're really the dominant kind of star in the universe. They really, a whole bunch of them. They start, the lowest sort of mass is just a little below 1/10 of a solar mass. You can try to see, you can see the masses are written. It's kind of hard to see them, but there's the 0.03 solar mass, 1 solar mass near where the sun is, etc. as you go up. It also, the green lines tell you how long things live when they're on the main sequence, right? 10 to the 11th years, 10 to the 10th years, that is 100 billion years, or 10 billion years for the sun, and much shorter as you go on and up, right? And then above the main sequence are the giant stars, and then down below the white dwarfs. You can see these faint lines, gray lines across. That's the size of the star, how big the star is as it goes up, right? So the smallest stars, the dwarfs are sort of about 1/100th the size of the sun. Right? And the slash across the middle that passes right through the sun is the sun size, and then you get up to the giants, which could be 1,000 or 10,000 times the size of the sun. Another way of looking at this is here's the history of the sun, as how we think the sun starts. It's born as a star on the main sequence. It will go through a giant stage. And there's complications as various ways that it starts burning stuff. And so it has sort of like 2 spots where it stops within the giant part of the HR diagram, the first red giant phase and the second red giant phase. And then it will go through this planetary nebula phase where it blows off its outer shell and become a white dwarf and eventually die and fade out. Across the bottom is a sort of versus time plot of this, right? You see the sun born, and if you were here last week, you talked about the birth of stars. I'm not going to talk about that, except briefly. And it stays on the main sequence for a long time, about 10 billion years. It goes through a relatively brief giant stage. It becomes a planetary nebula, and it gradually fades into a white dwarf. Just to note that we think the sun, so this is all, today, this is all done with computer models, where you can put in all the stuff about how nucleuses burn and all this other stuff. Very highly accurate, very well done, and showing how this all works. And so we're pretty confident that the sun is about 4.5 billion years old. That also jibes with the age of stuff we find here on the Earth. We don't find things, we don't find anything older than that lying around here. And it has about 5.5 billion years to go before it will turn into this red giant, and it will be uncomfortable to be here at that stage. There's stars that are heavy, have a different path. If they're about 8 times the mass of the sun, something else happens. When the core becomes so compressed by gravity, a new form of nuclear burning can open up. And it's crazy to think about this, but what happens is gravity gets so strong, it compresses the electrons that are in the atoms into the nucleus. They combine with the protons and make neutrons. Right? And that suddenly releases a huge amount of energy. There's actually energy released by that process. This production of neutrons releases so much energy. And there's a cartoon here, the cartoon showing what happens. You can see the onion star. If you look then closely at the center, you can see it's starting to collapse. But then this red thing represents the production of neutrons and then the energy piling back out, and you can see a collision happens between the infalling stuff and the outgoing stuff, and you get a giant explosion. The most famous of these is called Supernova 1987A. This is how supernovae are named, right? They're named by the year in which they went off, and then the first one in that year is called capital A, the second one is called capital B, et cetera, et cetera. And then you start adding 2 letters, et cetera. And, so this was the first supernova that was observed in 1987. It was observed in a local neighboring galaxy of the Milky Way, the Large Magellanic Cloud. And since then, people actually saw the progenitor star of this, and it was a blue supergiant. Right? There were archival images of this thing, and so we know that this follows exactly how I've described it. It was a big star that was in this onion stage, and at the end it exploded. Right? And we've been following the cloud that it released in the explosion for, essentially for 20 years. Right? And the picture I have here is an X-ray image of that cloud. And you can see one, and it's about a 14-year sequence from 1992 to 2006. You can see it getting bigger. And you can see it interacting with the interstellar media. As it collides into other stuff, you see hot regions form. And that's what's happening down at the end. It's colliding into the interstellar media, and stuff is starting to happen. I also inserted there a Hubble Space Telescope picture of what that thing looks like in the visible. Right? In the visible, you see this sort of flying saucer thing. Again, you see sort of hot spots where it's colliding with the interstellar media. So we want to understand what those clouds look like, and we can do that with spectra. Right? And so now here is hydrogen. Right? You can see that it has a specific color, and if I put it into the path here of the camera, you see specific lines. Right? That's because of the structure of atoms and quantum mechanics and all the other stuff. And so you can see that every element produces a specific fingerprint of these lines. Right? There's hydrogen. Let me turn on helium. And when I put it in the way, you see a different set of lines. Okay? And I got one more. This one is especially rich in the visible, with lots of lines through the visible, producing this distinctly red color. Right? So we want to figure out what's in those clouds. And we can use this technique to do that. Right? And this technique is called spectroscopy. And so you do that with, this is the cloud of supernova 1987A. And you can see it's filled with the building blocks of life. On the right there is carbon. You can see oxygen in the middle. And there's hydrogen lines that are very strong. You can see iron, the ash of nuclear burning there, neon, all the things that the star produces is there. So supernova provide the basic building blocks of life. Right? Without them, bluntly, we wouldn't be here. Right? This material that produces life, that life depends upon, is made in stars. And it gets out of the stars when the star explodes and spews that material out and to feed the interstellar medium. Supernova explosions, the shock that sends out into the interstellar medium is actually what starts star formation. Without that, stars wouldn't form. And we can see that in a specific example of the Trifid Nebula, which is Messier Object 20, and it's quite close to a supernova remnant known as W28, which I indicated with the little star down here in the lower right corner, excuse me. The Trifid Nebula is beloved by teachers of astronomy. because it has all the kinds of nebula in it. Right? The red is the emission nebula, and the blue is the reflection nebula. And then you can see dark parts, which are dark nebula, things that are not hot, that don't have light illuminating them, and they create blank regions. When we look at the star, look at this nebula, we can see there are new stars being born inside of it. There are regions that are collapsing, becoming denser. A and B, they're located on these things. And you can see that it's all sort of ignited by the shock wave caused by the supernova that occurred. It's not clear when it occurred. We aren't sure when W28 occurred. But it has made these shock waves going through this cloud of interstellar gas and dust and started the formation of star systems. Okay? We can show that shocks lead to collapse in this other cool demo. So you can see this innocent can sitting there. Think of the can as an interstellar medium. It's actually held. It's supported. These clouds are also a balance between gravity and something else, and the something else is usually spinning. Things that are spinning around, they like to stay spinning around, and that's what leads to stable configuration, spinning in gravity. The solar system, for example. The planets are spinning around the sun, and that means that they're not falling into the sun. Right? So a cloud is typically rotating around itself, keeping it from collapsing, but then some shock comes in, and the shock is right? Tiny little shock suddenly leads to collapse. Well done. And that's exactly what's happening in a cloud like the Trifid Nebula. We have local evidence that our own solar system was created by a nearby supernova remnant. The sun lives near the center of a region called the local bubble. It's about 300 light years across. It's an area of basically underdense interstellar medium surrounded by an overdense, and it's spherical. This is exactly what supernova remnants look like. This one is way bigger. The one from 1987A has gotten to be about 3.5 light years across. This one is about 300 light years across. You can see this supernova that happened somewhere near the center of this, that is quite close to the sun, probably created the star formation of all those stars that you can see listed on that. This isn't the only one we see nearby. This is sort of pulling out five more times, about 1,500 light year across, and you see more of these spherical regions, imaginatively named Loop 1, Loop 2, and Loop 3. Right? So the evidence is that our local region is riddled with supernova remnants, and that the supernovas that created them ignited the star formation in our local region. You can see others that don't have names. You can see other exciting features in the interstellar media. The Aquila Rift is my favorite. It's just a great name for something. The red things tend to be dark nebula. They're so dense that it's hard to see through them. Okay, so supernova provide the building blocks of life, and they provide the cradle of life. So I have a question. Some stars will get a second act, and there's a reason they get their second act. And I'm gonna ask this question: do you know how many stars live in multiple star systems? It's hard to answer because what we've been discovering over the last about decade or so is that the dimmest, the red dwarf stars, they tend to like to live alone, and they're the most dominant star in the universe. But it's hard to count them because they're dim. Right? So that's leading to uncertainty. Our best guess is about half of stars live with a companion, between about 40 and 60%. That's pretty high. That means, and so what happens in those systems? Well, here's an artist's conception of a white dwarf with a sun-like star as a companion. And what happens is stars are constantly losing a little bit of their mass. I mean, you can look at the sun. You've heard about solar flares and things like this. And the solar wind. There's constantly a stream of stuff leaving the hot surface of the star. right? And that stuff, if you're in a system with a big gravity well like a white dwarf, will accrete onto the white dwarf. And that's what the picture shows. An accretion disk forms, and that's just because of the physics of gravity and spinning things. If you're attracted by gravity, you tend to start spinning, and it tends to form a disk. If I have a white dwarf and a companion, and by the way, I put skull and crossbones here because if I'm lying to you about something, this is what I'm lying to you about, right? Because we're not exactly sure. This story that I'm going to tell right now, we're not exactly sure if this is how it works. The white dwarf accretes matter from its companion until something that we're not entirely sure of happens. What we seem to understand is that it gets above a certain limit in mass, and it's called the Chandrasekhar limit. Chandrasekhar was an Indian physicist. He actually worked with Eddington, and when he was 19 years old, he wrote this paper describing this, and it's amazing that a 19-year-old could do this. And what he noted is that if the white dwarf gets above this limit, gravity wins again, and it starts to collapse. And that collapse initiates a new kind of nuclear burning. So there's the white dwarf, and you can see at the center of it, when it passes the Chandrasekhar mass, something happens. That is, we start to burn this material, and the material heads on out and breaks out into the outer part of the star. You can see this is a simulation done on supercomputers in high resolution. It typically takes months of supercomputer time to do this. This is partially why we don't completely understand what's going on here, because it's really difficult. It's consumed about half the star here. And it'll finish by eating the entire star. So the sequence that I showed you there, this all happens in about less than half a second. Okay, so this explosion is called a type 1a supernova. The entire dwarf, which is mostly made of carbon and oxygen, that's what these objects usually end up as, is consumed in a fraction of a second, and it produces some of the brightest explosions in the universe. The key to why these things are so valuable to us and so interesting is they happen at a specific mass, right? This Chandrasekhar mass is when this happens, and thus they're bright. So you have the same amount of material that you're burning, and their brightness is pretty much uniform. These make these incredibly valuable to do the standard candle technique. And so my illustration of this used to be to say, okay, think you have a 100-watt bulb, right? I can't say that anymore because, well, most people in this audience probably know what a 100-watt bulb is. But when I'm talking to my students, I say a 100-watt bulb, and they say, what the heck is a 100-watt bulb, right? I don't know what that is. What are you talking about? But if you had a 100-watt bulb and it was close to you, it's bright. But when it's far away, it's much dimmer. And you can basically use that to figure out how far away something is if you know it's a 100-watt bulb. Well, type 1a supernovas are just like that, a standard candle. And because they're so bright, we can measure intergalactic distances with them. And thus we can start to actually look at the entire cosmos with them. I want to take a break and give you a review of stellar evolution on a page. I love this graphic. Basically, we teach a class, typically also to those juniors in physics, of how stars work, and it takes a whole semester, but you're going to have it here in one page. One page is going to be how it works. Stars form out of gases, clouds that collapse. They're in the center is something called a pre-main sequence star that eventually gets hot enough and dense enough to start burning hydrogen. if it's enough mass, right? If it's low enough mass, if it's sort of like 1/100th of a solar mass or less, it's not going to ever burn anything, and that's called a planet. If it's from about 100th to about 1/10th of a solar mass, an object called a brown dwarf will form. That becomes hot enough and dense enough to burn a isotope of hydrogen called deuterium, right? And over the last 10 years, we've discovered a whole stack of these things, and it's become a whole new branch of astronomy, understanding brown dwarfs, how many of them are, et cetera, like that. But once you get about 1/10th of a solar mass, you become a main sequence star, and we talked about those. You're happily burning your hydrogen in your core from about 1 million years to about 100 billion years, a trillion years or so. What happens next depends completely on your mass. If you're like half a solar mass, you never are even able to burn helium in this star, and you become what's called a helium white dwarf. That thing will not be able to turn into a type 1a supernova. It's too small, and it'll end its life as a black dwarf. The medium mass star to about half a solar mass to about 8 solar masses, it'll go through the red giant stage, planetary nebula, and form the carbon-oxygen white dwarf. If that one happens to live with a companion, it will go through an accretion phase. I skipped over the possibility that it'll go through nova phases and stuff like that because it's not really important. But at some point, it turns into one of these giant explosions, the type 1a supernova, with nothing left behind. The heavy stars, they go through the supernova, the supergiant phase. They will explode as core collapse supernova. On this graphic, it's labeled a type 2 supernova, but core collapse is more correct. And what happens to that depends exactly on its mass again. The ones that are from about 8 to 40 solar masses will produce a neutron star in the middle. That big ball of the thing that powered the supernova explosion will basically produce this giant bunch of neutrons. And this giant bunch of neutrons is what we call a neutron star. And they've been observed as pulsars, and that's probably worth another Saturday morning physics talk. It's a great story. And then if they're heavier than about 40 solar masses, the remnant even goes further. Another thing happens, and it collapses into a black hole. And black holes are objects that are probably worth about 10 Saturday morning physics talks because they're so mysterious and so interesting and such excited about what's stuff. The key observation about type 1a supernovas was made by Mark Phillips in the early 1990s, and he made this great graphic that gets shown over and over and over again, where he noted that if you brighten up quickly and then fade quickly, you're not as bright at the top as the ones that take longer to brighten up and then and then dim off, right? And so the plot at the top is what's called a light curve, and it shows the brightness versus time. And you can see the ones that go up and down fast are less bright than the ones that take longer to go up and down, right? And you can take that into account. It's called the stretch luminosity relationship. I love that. And you can basically turn type 1a supernovas into a fairly precise measurement of intergalactic distances from the 20%, if you didn't know about this, to about 7%. And once you get below 10%, you're actually able to do real science, right? And so people said, hey, we can do real science with these things. And in fact, there was a very famous piece of real science that people immediately thought of. So this is the proof that we live in an expanding universe. It's from Edwin Hubble in 1929. It's so famous that the diagram itself, which is across the x-axis there, the distance to nearby galaxies, and on the y-axis there is how fast they're moving towards us, if it's away from us if it's positive, or towards us if it's negative. He noted that all the galaxies are moving away from us. Right? Once you get away from the very nearby ones, they're all moving away. And the further away they are, the faster they're moving away. And he boldly drew that line, linear relationship between how far away you are and how fast things are moving away. Right? The diagram is so famous, it's called the Hubble diagram. The slope of the line is called the Hubble parameter. So that indicates that it's really important, right, when you get names attached to it like that. And people immediately said, hey, let's do this with type 1a supernovas. So people typically ask us, why does this tell you that the universe is expanding? Well, we have a demo. All right, and so here we have the universe. You'll notice it's filled with stars and things. Think of each of these as galaxies, because it's not stars that does this, it's actually galaxies. And as the universe expands, and where's our where did it go? It's right here. You can see what happens. Whoops. Sorry. All right, there we go. So what you can see happening is all those little stars are getting further and further apart, and each star gets further and further apart from all the other stars. And if you were sitting on one of these stars and you were looking out, you'd see that all the other stars are moving away from you. And in fact, you'd discover that the ones that are nearest to you are moving slower than the ones that are further away from you, because as the universe gets bigger and bigger and bigger, that's just how things will work. Because and so this is exactly what's happening with our universe. It's slowly expanding, and I know I have everyone in suspense. Will it explode? I'm told that if I leave it long enough, it explodes, but we won't do that. We'll leave it there as a possible excitement. So this diagram is terribly, terribly important. It really is the proof that the universe, we live in an expanding universe. It suggests that in the past, the universe was small and dense, and it has evolved to today's universe, which is large and mostly empty. Right? This is what we mean, what astronomers and physicists mean when they say the Big Bang. Right? The Big Bang means the universe was once small and dense, and it has exploded into the empty and big universe that we see today. There's more evidence for the Big Bang. This is worth another Saturday morning physics talk, or probably 3. The cosmic microwave background, which is a glow of microwaves that you see if you look into the sky, it's the leftover remnant of the explosion. When the explosion happened, it was very hot, and it started to cool off, and at some point, the light broke free and filled up the universe. And today, that light is the cosmic microwave background that we've observed with increasing precision over the last 20 years or so. Also, that the elements of the universe are dominated by the simplest things. Hydrogen and helium is a consequence of the Big Bang. And that basically says that, look, it's hard to form the heavy elements. You need to be dense and hot to get things together. But if the universe is expanding, well, what happens is only the simplest ones manage to form in the early part of the universe. And the more complicated ones have to be built in stars. Right? And so that's how our universe works. It started out as just a bunch of simple elements, but then stars formed, making the more complex elements and building life. I'll point out that at this point, the fate of the universe is not entirely clear. There are 2 paths. One is, look, the Big Bang starts this expansion of the universe. How does it do that? No one really knows. That's a mystery, so we'll just leave that. There is something that starts the expansion of the universe. But it now basically moves under the influence of gravity. Gravity is the only force that operates at such a big scale as the scale of the universe. So what happens is gravity is starting to act, and it starts to slow down the expansion of the universe. And it could actually be stronger than the initial kick that got it going, and the universe would start to recollapse. And eventually, everything we know about will collapse into maybe a single point. actually put a question mark on that because we don't really know what happens when it starts to get that dense. We have a name for this fate of the universe. What do you think it is? The Big Crunch, I heard. It's a pretty famous name. So indeed, it's called the Big Crunch. Right? And if Fred were here, I'd give him a nod at this point. Fred Adams, Professor Fred Adams, wrote the definitive paper on what could possibly happen to the universe, right? And the Big Crunch was one of those. And I'll get to the next one here on the next set of slides. The other possibility is the expansion is too much for gravity, right? The galaxies just keep running away. It keeps going slower and slower and slower, but it never stops. And what happens is the universe becomes less and less dense. Stars, although they live a long time, they will start to burn out, right? I've showed you that. The last thing was dead stuff, right? They were black dwarfs, neutron stars, and black holes. These things are dead, right? They're just dead. There's nothing. They're not burning anything. They're not producing energy. They're just dead things. And so eventually the universe will be filled with dead things. And it starts to get colder and colder and colder and colder. And eventually it freezes to death. What's the name of that? The Big Freeze is a good guess, but this was originally thought about in the 1980s, and there was a movie, so it's called The Big Chill. Okay? Okay, so now to understand how we describe the universe on the cosmological scale, so we can figure out what will happen to it, cosmologists make this diagram. And the diagram has on the x-axis the mass of the universe. And it's labeled with big capital omega, little m. And if you get to 1, that's enough to force the Big Crunch. Right? On the y-axis is, well, it's either attractive stuff, extra attractive stuff, if it's negative, or it's repulsive stuff. Right? And this was invented by Einstein back when he first considered cosmology, and he said, well, look, and at the time, this was in like 1918, and people did not know that the universe was expanding. So he was trying to explain why the universe is static. And so he says, well, look, there needs to be some repulsive thing to fight back against gravity. And he called it the cosmological constant, and he labeled it with capital lambda. So on the y-axis is omega lambda versus omega mass. Right? And there's a dividing line between Big Crunch and Big Chill. And you can also find places on this where the Big Bang doesn't happen, right? If you're in the upper left corner there. It also tells you where you sit, and there tells you what the geometry of the universe is, right? The line, the diagonal line, is that the universe is flat. Now, if you think in 2D, that means it's like a piece of paper and it's infinite. You go out, you always go away, and you never get closer to where you started. If you're below the line, you're a closed geometry. So in 2D, that would mean you're like living on a ball, on a sphere. So you would go out, and you'd eventually come back to where you started. Above the line, it's the open geometry, and it's exactly the opposite. Good. Because, yes, it's hard to think about. What does that mean, exactly the opposite? It means you go out and you always get further and further away, faster and faster and faster. Mathematically, it's easy to write down. To think about how it looks is hard, right? You need to be I have difficulty thinking about how it looks, but that's what it means. So this diagram really tells us about the geometry of the universe and the fate of the universe. So people did what I said. They said, hey, look, type 1a supernovae are great. They're standardized candles. Let's go make the Hubble diagram with type 1a supernovas. This was done in 1998 and 1999, and it was a clear observation of a repulsive cosmological constant, which now gets the name of dark energy. The the plots over there show it. You can see it's hard to tell, right? Maybe the bottom plot shows it best. If you're above the line at 0, that indicates that you have some repulsive cosmological constant in the universe, some dark energy. This observation has been confirmed. Other alternative explanations for what's going on here have subsequently been ruled out, including one that I did. Which makes me unhappy, but that's what happens. This seems to be what's going on here. And in fact, this has become so embedded that the people who did that observation in 98 and 99, Perlmutter, Schmidt, and Rees, were awarded the Nobel Prize. And I mention that specifically because Adam Rees will be talking at Wayne State in April. He'll be giving our Vaden Miles lecture, which is our big public lecture that we have once a year when we try to get Nobel Prize winners. And Adam has, and I've just written a paper with him, so he's graciously come. So look in your email feeds or whatever, and come to that lecture. He does a great job. He'll give a great talk. He is currently blowing up modern cosmology by doing a new measurement, and I hope he'll talk about that in April. So if you make this diagram with the supernova data, you can see it implies that we're headed towards the Big Chill. We live in an era where the Big Bang happened, etc. What makes it very interesting is that 2 other measurements on cosmological scales are in concord with it. And so our modern model of cosmology is called the concordance model of cosmology because 3 big things are in concord. The 2 other things are the map of the cosmic microwave background, which has been done very precisely. It implies that we live in a flat geometry universe. That's the green thing following the diagonal slash, the diagonal line. The other thing is the clustering of galaxies. If you actually look out at the universe, galaxies are not distributed uniformly. They like to cluster together. And that turns out to be a measurement of the mass of the universe, and it reveals that most of the mass of the universe is a form of matter that we don't really know what it is. And it gets the name of dark matter. And that's worth another 5 or so Saturday morning physics talks, probably even more because it's one of the most active areas of modern research into this thing. And you can see that's the yellow thing, vertical thing, and you can see the blue thing, the green thing, and the yellow thing all come together at a point that says there was a Big Bang, it happened about 14 billion years ago, and there will be a Big Chill in about tens of billions of years in our future. And the Hubble diagram with supernova was one of the first big clues that that's what was happening. I'd point out that this time that we live in is called the golden age of cosmology, and it reveals what's in our universe. It's about 5% ordinary matter, and the other 95% is a bunch of stuff that we don't know what it is. So it reveals that we don't really know anything, right? Or we know very little, or we know 1/20th of what we wish we knew. Dark matter, this mysterious form of matter that holds galaxies together, that we can see patterns of it in the universe, is about 5 times bigger as a makeup of the universe. Dark energy, if you use E equals mc squared to sort of put it on the same scale as mass, it dominates the universe. The universe is about 70% dark energy. There are countless explanations to what's going on here, what this dark sector is, but there's yet no decisive experiment, no decisive observation on the nature of the dark sector. So it is one of the most active areas of research in physics and astronomy today. What do we do next? Do we remain ignorant? No, we launch experiments. So I love this diagram. This is from the WMAP satellite. It was one of the first. It was the first satellite to accurately measure the cosmic microwave background, which is that green and blue thing. You might have seen it before. on this plot. This diagram is the history of the universe on a page. Right? It shows the universe being born in a quantum fluctuation. I wish it had a question mark because that's an idea. No one really knows if that's how the universe was born. It goes through a period of inflation. I wish that had a question mark because no one is really sure if that's what happened. It sounds pretty good and explains a lot of features of the current universe. It then passes through this phase where the cosmic microwaves are born. It goes through the dark age before any stars or galaxies form. And then the stars and galaxies start to form, and then structure develops. And what's probably one of the other enduring mysteries of the universe is, look, at the time of the cosmic microwave background, I could write down what the universe looks like on a page. But today, the universe has structure and scale, structure at every scale, from the smallest to the largest. How did that happen? How did we get from a simple, uniform universe to the complicated mess that we have today? Right? The answer to that might have to do with what dark energy and dark matter are and how they affect things. The red things are, how do we solve these problems? And I'll do them in sort of time ordering. I mentioned briefly that when the neutrons, the electrons crunch into the protons, you get neutrons, and you get an elusive particle called the neutrino pouring out. Well, in the early universe, just soon after the Big Bang, protons and neutrons formed, and a bunch of neutrinos formed also. And they are called the primordial neutrinos, and they streamed out and filled the universe at an earlier time than that cosmic microwave background came. Sort of about, I don't know, we think when the universe was, I'm forgetting, it's something like 50 years old or something like that. That's when that happened, very early in the history of the universe. So if we can get a picture of the primordial neutrinos, we would learn a lot about the even earlier universe. And the reason why I mention that is because they're here today. The room is full of them. Right? In any little in a little volume like this big, there's about 100. And so the room is filled with millions. Problem is they're so non-reactive, it's so hard to pick them up that we've yet to devise an experiment to observe these things. People are trying. There's an experiment at Princeton that's dedicated to try to find these things. I don't know if it'll work out. There's and then some of the things that are studying the rare behavior of neutrinos are starting to approach the level that they might be able to see the primordial neutrinos. And experiments that are searching for dark matter might be running into primordial neutrinos very soon. So I hope within the next decade, I hope I'm pessimistic about that, we'll actually see observations of primordial neutrinos. Look into the cosmic microwave background. We've measured its energy spectrum very well, but we have not measured its polarization structure. All light has, a direction that it's vibrating in. And if you can measure the polarization structure of the cosmic microwave background, it reveals something about the early universe. And so a bunch of experiments are being mounted to try to measure the polarization structure of the cosmic microwave background. Peer into the dark age and try to understand how do the first stars and first galaxies form. This is one of the science goals of the James Webb Space Telescope, which will be launched in 2 years. 2 years? Yeah. 2 years, and it's got powerful infrared sensors on board, so it can look into the dark age and see the first stars forming and the first galaxies forming. The other things are, two of them are stuff that I talked about already, right? Galaxy clustering, do that better, and supernova to get the expansion history of the universe. Those things, the idea is to just do those better. Right, and there's the signature project of that is called the Large Synoptic Survey Telescope. And it has a third thing that it wants to do called weak lensing, which basically mass causes light to bend. And if you look at lots of galaxies, you can see, and you do it very, very carefully, you can find the weak effects of the mass between you and that galaxy distorting the galaxy. And that's called weak lensing. And if you do that across the entire sky and deeper into the universe, you're able to measure the mass, how massive the universe changes with time. And you make a sort of 3D, a 4D map of the mass in the universe, right? It goes in time, too. And that will tell us a lot about the effect of dark energy and dark matter on the structure formation problem that I talked about earlier, right? And so each of those red things probably represents $500 million of effort that's going into this. I don't want to go away saying that we understand everything. There are a great deal of mysteries, and some, let me just highlight the ones that what I talked about here today brought up. Is supernova shock really what leads to star formation? The evidence is very, very strong for this, but we've yet to sort of have a smoking gun. A supernova, and supernova 1987A is the candidate, right? If we start to see a star forming in the shock, in the expanding cloud of supernova 1987A, we can check that off. Supernova expansion does, the supernova remnants and the shock caused by them leads to star formation. Where was the supernova that created the solar system? Right? We seem to live in the local bubble that looks like a supernova remnant. Where was that supernova? When did it go off? There are a couple candidates, but as yet there are no answers to that one. So back to the skull and crossbones, what is really the origin of type 1a supernovas? The story I told you is our best guess as of today, but we have yet to observe a system that explodes as a type 1a supernova. We've done it with core collapse supernovas. We see that large stars turn into supernovas, core collapse supernovas, but we have yet to figure out, we've yet to see a system that explodes as a type 1a supernova. There are a couple candidate systems, and if we just wait around a few million years or so, we'll get a lock on that. Basically, we need to get lucky, right? Things about cosmology. Why is the universe the way it is? Why is it the geometry flat? It could, why did nature choose that? Why is that the answer? Why is it dominated by matter? If we look out in the universe, we see that here our local universe is dominated by matter, and you look out, you find there's no walls between places where it's dominated by antimatter. So our universe is dominated by matter. Why is that? Is it really dominated by matter? We don't know what dark matter is. Maybe dark matter is some mixture of matter and antimatter together, and they somehow make things balance out. Because we don't know what dark matter is, we better admit that possibility. And probably the biggest question that worries me is, what is the nature of the dark sector? What is dark energy? What is dark matter? Some people say we can solve all those problems and make those things go away by just changing the way gravity works. That sounds great, but we've tested how gravity works very, very accurately, down to like 100 nanometers in scale and up to the scale of the solar system. It's hard to do experiments larger scale than that. So these people have said, look, on larger scales, maybe gravity works differently than we think it does. That sounds great, except it breaks general relativity. General relativity has been tested in more ways than just about any other description of a physical phenomena that I can think of, right? And it's clearly almost entirely completely correct. That is, we've never found anything that's at odds with it, and as far as thinking that it and how you would change it at large scales that we don't break what we know at smaller scales, it turns out to have been ridiculously hard, and no one's come up with it yet. Okay. So here's my summary of everything. I talked about supernova as the origin of life. They provide the basic building blocks. The shock formation from the explosion starts the formation of star systems, which I'll point out we live in, a star system. So it is the origin of life. And type 1a supernovas reveal the origin, the fate of the universe. dark energy and dark matter dominate the universe, and it will end in a big chill. Thanks. Thanks a lot.